Okay, so based on this two model, we already know how we estimate, but we still want to emphasize what do we mean by estimate the differences. Because the divergence for any given sequence is something we really want to understand, the distance. So when you start in the later part of the lecture, when we start doing the phylogenetic reconstruction, we need a certain data like a distance matrix. So that's something we really want to calculate. So we want to know if there's n differences, the small n differences in any given length of the sequences, and what's the proportion of differences. And at the end, we want to know like the degree of the divergence in the population and how do we estimate from this observation. Okay, this is the same sequence, but just assume we know all the process, like an experimental evolution approach. So for any given, say, bacteria strain or yeast strain, you can sample generation from generation, assuming you can sequence all different individuals in the population, and you get every snapshot of the mutation process showing on this slide. And on the right-hand side of the slide, just talk about all different changes. But the important part is to show you, as we start in the beginning of this lecture, is all the changes are not observable at the end of the sequence point. So all the mutations occurred in the historical time. But at the end of the sequence, for example, in the middle part, we have one sequence from A, change to C, change to T, then change to G. And the final state is a G, right? And the other sequence stay as an A. And what the observation you have is the GA differences. And that's the proportion of difference. As a counting method, you can count, this is a G, this is an A, they are different. So that's what we can do based on our observation. But the hidden information is the change to C and T. We were not able to know what exactly happening in the past. So all the estimation we are trying to do is try to estimate all the possible changes during the evolutionary time. And showing this diagram just to illustrate there are a lot of changes which cannot be observed just by simply pair the two sequences together. So that's the middle part, and we call that in the earlier slide I already showed multiple hits. So there are changes occur at the same time, repeatedly during the history. But at the end, we only see, we only can observe whether the sequences are the same or different. So there's a lot of changes cannot be observed by any given sequence comparison. And those are the mutations we would like to estimate based on the current status of the sequence. So based on the one parameter model, which we start with, then we want to look at the two sequences. And the two sequences we want to know is the proportion of the sequence which stay the same nucleotide. Okay, so when we start with the one parameter model, we say for a given time, the sequences stay as an A. So that's the same thing. Now we're talking about there are two sequences, and the two sequences now are at the A status. So they are the same. And they could be different, right? So the probability the two sequences are the same is because one is like they start with an A. So the observation is the ancestral sequence assumed it's an A. Now the two sequences evolved for a time period T. Then they are A, both are A. So the probability for that. So for one pass is the PA. That's what we calculate. Then there are two independent paths, right? For this path, evolve from the ancestral to the current A. And in the other path, from the ancestral to the other A. Then you have to multiply the two. So that's the P square showing on this formula. And for A, then but it also equally possible is from A, the ancestral state, to T in both lineage. So that's the second part of this formula. That's the P square, but now the notation is from the A status to T status. But still, they are the same. So in this formula, we are calculating the two sequences. Now they are identical in their nucleotide states. And the possibility for them is for any given nucleotide to the current states. So if we assume we all start with the ancestral A, now they could be the same as A, or it could be the same as T, G, or C. And that's the different components of this formula. Because there are two independent lineages, so the probability is always you have to multiply the two. So it's always P squared, then you add it in together. So you add all the possibilities together, then that's the overall probability for they are at the same state. So they are identical. We use I here. So they are identical at the observation time T. They are A, G, T, or C. So that's the observational. Then we say, okay, they are the same. So that's the I part. Okay, so this part is to talk about the sequences are identical. And the reason for that is because it's easier to calculate this way than X if they are different. And you know, if we calculate the identical probability, then the different one will be just 1 minus the identical probability. So that's why we start with the identical one. Just make an analogy that's like a heterozygosity. We calculate the homozygous, and 1 minus all the homozygous become the heterozygous. So it's very similar as that. So if we can calculate the identical status based on this formula, and we already know based on one parameter model, we can add it in all together, and that's the equation given to the IT equal to 1/4 plus 3/4 of e to the minus 8 alpha t. So the same thing, there's only one parameter in this formula. Then we can calculate the differences. And the differences will be 1 minus the identical proportion. So that's the proportion showing in the following slide. And we can arrange the formula because to us, we are more interested in the changes, actually the alpha. What is the alpha and what is the probability? So we can rearrange to a natural log. So you switch the parameters on both sides of the equation and you can get the formula at the bottom. So that's the thing we want to, at the end, we want to talk about. Why it's important? Because for any given sequence, if they evolve to two different status for a given time t, and that's the independent evolution, right? They diverge from the ancestral state and now become the two independent sequences. These two independent sequences could be the sequence in two different species or the sequence for the two individuals in the same population as the sequence between you and me. Okay, so that's what illustrates here. But the important part is for any given time, the changes should be 3 alpha t. 3 alpha is the change probability, right? It's the alpha times 3 different status, times t is the evolutionary time. And usually, we forget there are 2 independent ones. So there are 2 3 alpha t's. So that's the diagram showing on the top. Just try to remind you the 2 sequences evolve independently. And that's the evolutionary time, k. That's the difference, that's the changes for k. So at the bottom, you can read the words afterwards, but the important part is the k equals to 2 times 3 alpha t. So that important part is the 2. So 2 independent lineages in this formula. Then we want to estimate the k. Remember on the previous slide, we can rearrange the formula to the 8 alpha t equals to the natural log of 1 minus like small divided by 3 times the p, that's the probability. So that's the bottom part, the minus equal log, neutral log of that formula. Now we want to know the k, that's the divergence between the 2. And k is equal to 6 times alpha t, right? So that's the formula here. Then if we put the 2 together, then we'll be able to calculate. And using this formula, we can calculate or estimate the k. That's the estimate we want to do given the 2 sequences. So that's the like a practice we do in a lot of time. So that's why we spend a lot of time talking about the metrics, the methods, the models. Then we want to introduce at the end, or at least in practical, we want to estimate the k value for any given 2 sequences. And at the bottom of this slide, just show you the observed number, which we mentioned last time, is the p. P is very easy to calculate or to count. As you have 2 sequences aligned, then you can count number of changes, and that's observed number. And the whole reason we went through the whole calculation is to estimate all the possible changes during evolutionary time. So I already repeat this last time. So this is how we calculate the k value between the given 2 sequences, assuming they have a like common ancestor back to like a time t. And I don't want to go through all the calculations about the 2-parameter model, but it's very similar, and just given the different transition and transversion rate. So here we have 2 observed number, the big P and big Q. So these 2 numbers are observed the proportion of transitions and transversions. So in the previous slide, when we used the 1-parameter model, we only estimate the overall differences, that little p. But now, since we want to separate the transition and transversion, so when we count the number of changes, we also have to recognize, is this a transition or a transversion? So after we do that, then we'll have 2 observed numbers. One is the frequency or the proportion of transition. The other one is the proportion of transversion. So just from 1 differences, regardless is transition or transversion, now we want to separate the 2 for transition and transversion. And the same thing, we can calculate the divergence or nucleotide substitutions between the 2 sequences. And a few of you came to me last week worried about the mathematics. Okay, first of all, when we have a test, I won't ask you to derive the mathematic model. But I do want you to understand the differences. So if I ask you what's the difference between 1-parameter model or 2-parameter model, you have to be able to respond to the question. So that's the central message. And even later on, you saw people use 12 parameter model. What does that mean? So you have to have the ATGC diagram, that square, then you think about all the possible changes. And transition and transversion, just a very simple illustration about how we separate the different changes, right? But you also probably know empirical data also show the rate of each change are quite different. So you can add more parameter into the matrix. So adding more parameters, you get like a different number parameter model. So that's the basic. So in the class, we only talk about 1 and 2. In your textbook, we'll talk a little bit more about more parameters. And we never ask you to really derive the mathematical model in class or in your test. But I do want you to understand the differences. And just to illustrate the differences, this is the example in your textbook. We want to look at the two models here. And the formula list on the top of this slide is the one from previous slides. And we want to give an example, a simple example like this. If we have two sequences, and just by aligning them, we observe 20 transitions and 4 transversions. So that would be an example. Then using the number here, we could calculate the K value for these two sequences, the substitution rates for these two sequences. So then down bottom is the results using either 1 parameter model or 2 parameter model. And it's very simple calculation, right? It already give you all the numbers. And most I would do, I would give you 2 sequences and ask you to count the numbers in your a written test. And it's pretty easy to assign transition and transversion from the sequence. Then you can calculate the P, the small p, that's the overall changes, observed changes, proportion of the observed changes. And you can estimate, you can count or calculate the big P and big Q. That's the observed transition and transversion rate. And that's the calculation here. Then K is just putting those numbers into the formula. So that's the value of K. So with that, you can see in this example, the K is exactly the same. The estimate K is 0.13. I say, what? You use a different formula, you get the same answer. Okay, let's look at the different example. So in this example, you see actually there's no differences, regardless which method you choose. And when the sequence is very similar, the changes are little. Actually, using different model doesn't really affect the end result that much. So that's basically what we want to. Then why you want to introduce a complicated model or even more complicated than the 2 parameter model? Let's look at the other example. So in this example now we have 50 transitions and 16 transversions. The same thing, you calculate the proportion of changes for each classes. Then you calculate the K value. Showing here the K using 1 parameter model is 0.43. And the other one, the other way, we calculate by 2 parameter model, we get the number of 0.48. Okay, so what? The two numbers, first of all, the two numbers are different. And although it looks like small, it's like a 0.05. That's the difference between the two estimates. But this example just want to know, not always, any sequence, any given 2 sequences, when you calculate by different models, they are not always the same. So they will be different. Then the differences could contribute to by the number of changes, especially when the two sequences are quite diverged. Then the amount of transition and transversion are large. Then in this case, it's probably better use more complicated model like a 2-parameter than just using 1-parameter model. So this is basically what we want to say. And now the 2-parameter model is the most popular one. So everybody, almost no people start using the 1-parameter model. But actually, sometimes the calculation will give you exactly the same answer. But a lot of time when we start calculate the substitution rate, most people will use the 2-parameter model to start with, because the transition-transversion rate differences is quite obvious for most of the people, and also for most of the organisms, we observe the differences in transition and transversion rate. So that's basically what we want to that you know in this part of the lecture. Then your textbook also tell you a little bit about all the assumptions. Because when we think about the evolutionary changes, the nucleotide change from one state to the other, remember last week we started with the position A, and the A changed to different nucleotide states, or A didn't change, right? That's what we try to explain all the possibilities. But we never talk about what's the neighboring sequence with A. So, and we don't really care. It's not we don't really care, or they won't affect. It's just to make the model simpler, we have to assume each nucleotide change independently to their adjacent sequences. So the position A at the nucleotide A at position 6 will have the same probability to change to all the other sequences as another A at a position like 100. So each site evolves independently, and also the neighboring sequence, the environment, doesn't affect the probability for its evolutionary change. So that's basically the assumption we made to estimate or try to estimate the multiple hits or the substitutions. Then the substitution matrix, the one I show you with ATGC on it, then it doesn't really matter like whether it changes from time to time. We use the same matrix over a long period of time. So once we choose the 2-parameter model, actually we assume the transition and transversion evolve at a different rate from time 0 to the present time. So that's what our assumptions are. And of course you can argue they are not entirely true. It means like it's not like 100%. The sequence could change, mutation rate could change. Why do we know mutation rate could change? Because now we can estimate, actually start from the evolutionary experiment, we can estimate the evolution rate or mutation rate from different organisms. So we know the mutation rates are different from one organism to another, even they are close related. So in that case, the changes over evolutionary time are not constant. But in our simple model, everything is constant from the beginning to the end. And every site is independent to all the others. So that's the basic assumption we use, and we use that to estimate, to try our best to estimate the substitution rate for given sequences. So just bear in mind there are assumptions behind those models.